There are about 100 billion stars in our Milky Way galaxy, so there must be at least one planet. As a rule of thumb, there should be at least one planet for every star. In fact, there are more. For example, there are 8 planets associated with our Sun. The planets of the Milky Way are difficult to count, but the data of scientists vary, and the range is quite large, from 100 billion to 3.2 trillion planets. However, it has recently been found out that there must be more planets, at least 2 trillion, but these planets are disappearing. To give you an idea of the scale of the loss, our galaxy has lost 20 times more planets than stars. For a long time, scientists didn't understand what eclipses were and where many planets went. Maybe they exploded or vaporized in space? No, they are still protected, just not attached to their stars. Such planets are called outcasts, orphans, loners, vagabonds, etc. Essentially, they are just like a regular planet. They are not attracted to a star or other planets. Saviors move freely through interstellar space in the galaxy and orbit around the galactic center. They come into existence because of a deorbit or as a result of some cataclysmic event. If our Earth were to collide with a large interstellar object, it could be thrown out of orbit and even out of our solar system, and then the Earth would be thrown out as well. But why do ugly planets disappear? Scientists have somehow managed to find them. It's true, but it's very difficult to find such a planet. It's very dark. The stars are flying in space. It's like looking for a nail in a completely dark room. Astrophysicists detect galaxies using the microlensing effect. This analogy can be compared to a situation where a planet's gravitational pull changes the brightness of its background star. Imagine a car standing in the middle of the dark with its headlights on. The image is stable and will not change, but if a person passes in front of that car, we will see them as the lights change. Actually, exorcists are found in the same way, and then fly away into the unknown. By the way, this is another reason for their disappearance. It's almost impossible to determine their exact location. It's not a planet tied to a particular star in a particular orbit. And now you might be surprised to learn about the evictions. Are they a threat to our system and planet? With trillions of planets roaming the galaxy and ready to crash into other planets at any moment, it's dangerous. But don't worry, we probably have nothing to worry about. Our galaxy is huge, and there's room for even 1 trillion rogue planets. Scientists estimate that the probability of a rogue planet forming in the solar system within the next 1,000 years is 1 in a billion. It's just a solar system, and it's huge. It's not a given that if an exorcist gets close to Earth, it will destroy it. However, close contact with the outcasts could lead to major catastrophes. The complete destruction of the Earth could only happen through a collision, but the likelihood of that happening is very slim. But it is even possible. The number of people leaving is increasing. About 10 years ago, scientists counted about 200 billion such planets. Now there are several trillion. So the real number of such planets could be many times larger. But let's not talk about the scary stuff. Let's talk about other planets that can't run away from their star. They're much easier to find. Most importantly, they can be properly verified. So, last year, scientists discovered an interesting planet they named LP79118d. All exoplanets have such complicated names and numbers. Externally, it looks like some sort of hybrid of the planets Coruscant and Mustafar from Star Wars. Incidentally, like Mustafar, the planet is volcanically active and very hot. At the same time, there may be life on the planet. The trick is that one side of the plate always meets the star, and it's impossible to stop there. However, on the other hand, volcanic activity can preserve an atmosphere and even condense water. In addition, the planet is located on the inner edge of the habitable zone. This means that you can live on LP. The planet is 90 light-years away from us. So, who knows? Maybe in hundreds of years we will go there and replay the legendary duel of Obi-Wan and Anakin in new locations. And yet, for now, these are just dreams. We can't get to faraway places yet, but we can travel to asteroids, at least with the help of drones. Some people say that asteroids are useless and dangerous pieces of silicon and iron that want to crash into something. But I will say that asteroids are useful. First, they contain lots of minerals that can be mined. Second, some even have organic life. This was recently confirmed by a discovery by scientists. They explored the near-Earth asteroid Ryukyu with the help of the Japanese spacecraft Hayabusa 2. It has collected samples from the asteroid several times before, but last year it discovered something new there. Primitive organic matter, amino acids, carbohydrates, and mineral particles. All this material survived in space because it was deep inside the asteroid. Wherever radiation reaches, these finds predate the formation of the solar system and are called pre-solar grains. Some astrophysicists call them seeds. But what's the point of this discovery, besides sounding cool? The fact is that this is how life on Earth began. The organic molecules that led to the development of life on our planet could have gotten here via ancient asteroids, meteorites, or comets. If this is confirmed, we can officially call ourselves aliens. After all, life on Earth came from the outside. But still, don't be fooled by asteroids. First of all, they are dangerous. And when news comes about another asteroid that is supposed to pass close to Earth, we all worry. What if the asteroid hits the Earth? What do we do in that case? Send commandos with a nuclear bomb on it, like in the movie Armageddon? No, there's no need to repeat the heroics of Bruce Willis's character. An asteroid can be moved or slowed down by a spacecraft, and a recent epic mission proved it. The mission was called DART, and its goal was to see if a collision with a spacecraft could affect an asteroid's orbit in any way. Scientists assembled a large vehicle, collided with the asteroid dimorph, and sent a probe to it. Most people thought this was pointless. How could a probe affect an asteroid weighing 5 million tons? It would be like trying to stop a car with a tennis racket. But the mission was accomplished. The probe picked up speed and crashed epically into the dimorph. The asteroid didn't disintegrate, but it shortened its orbit around a second asteroid, named Didymus, by 32 minutes. Scientists expected the harvesting to stop for 7 to 10 minutes, so the study exceeded expectations. And even if the asteroid is not destroyed, as in the same Armageddon, it is a big discovery. Humans were able to artificially alter the motion of a celestial body for the first time in history, and also made sure that it was possible to protect the Earth from meteorites by correcting their orbits with probes. Here's another thing. Google has an interesting passphrase. If you type Darth Asteroid or similar keywords into the search engine, a small arrow will fly across the screen and crash into the page, shattering it. Try it yourself and let me know in the comments if it works. Asteroids, organics, new planets are all cool. But mostly, we expect something more from space discoveries. Intelligent life, aliens, unknown life forms. We want to find something, and it seems scientists have found it. About a year ago, they detected a repeating radio signal from a red dwarf system called YZSETI. The signal is believed to be coming from the planet YZSETI. What's so interesting about it? Scientists often find different signals in deep space. Yes, but this time, they believe the radio signal may be generated by the interaction between the magnetic field of a rocky exoplanet and its star. This magnetic field is particularly interesting. Astrophysicists believe they help maintain a life-supporting atmosphere, protecting the planet's surface from high-energy particles and plasma emitted by the stars. In other words, this planet may be inhabited by the same intelligent beings or even advanced humans as planet Earth. Of course, it is impossible to know for sure. The nets are far away from our neighbors, 113 trillion miles away. But don't give up hope. Apparently, intelligent life exists on Earth, and the findings show it. Someone from the outside is definitely trying to communicate with us, and a very interesting observation can attest to that. Late last November, scientists discovered the highest energy cosmic ray particle in decades. It's called the Amaterasu particle in honor of the Japanese sun goddess. To give you an idea of how powerful this energy flow is, a single particle, 1,000,000 times the best achievements of the Large Hadron Collider, is accelerated to an unimaginable force. Interestingly, scientists traced the particle's path and found that it was nowhere to be found. Nothing happens in the part of space that receives the energy charge, can release energy of such force. But who could have sent it? Aliens detecting us? Our advanced doppelganger from a parallel universe? Or did the signal somehow miraculously come from a black hole? There's so much we don't know about the cosmos. Anything is possible. About black holes. Astrophysicists recently discovered a record black hole, at least the oldest in the universe. Amazingly, it's 400 million years younger than the universe itself. On the scale of the universe, that's nothing. The hole is located in the galaxy GNZ11, which is one of the most distant in the universe. It's 100 times smaller than the Milky Way, and the record black hole is several million times more massive than our Sun. Consequently, the black hole is holding back the growth of the galaxy. It eats up a lot of matter and slows down star formation. Perhaps the galaxy isn't too happy that it hasn't been given free rein. But the same thing is happening in our Milky Way. Don't think that black holes are very far away. At the center of our galaxy is a supermassive black hole called Sagittarius A. It has even been photographed with a telescope. This giant is 1,000,000 times larger than the Sun, but behaves strangely. For a long time, Sagittarius A was considered a calm black hole. It didn't behave that way and didn't assimilate matter. But recently, it's woken up and started eating matter. Maybe even stars. But it's not a threat to us. The black hole is 27,000 light-years away from us, so it can't devour us. Look at this red spot. What do you think it is? Another black hole? Maybe some kind of bright quasar? Maybe it's a little bit of both. After all, this is a galaxy, and we're dealing with another record breaker. What you're seeing is the most distant and oldest galaxy in the universe. It is 13.5 billion years old. It turns out to be older than the black hole that set the record. It formed just 300 million years after the Big Bang. Looking at this picture, we see the young universe. Besides being another interesting discovery, it's also a mystery. Scientists still don't understand how the galaxy formed so quickly. According to one version, the galaxy, incidentally named HD1, is unique in that it can form stars at an unusually high rate. This galaxy is home to the first generation of stars in the universe. According to another theory, the rapid formation may be due to an anomalous black hole. It's difficult to understand. It's probably as hard as realizing we have pictures like this. How can you photograph something so far away? The thing is, this picture was taken with the James Webb Telescope, which is considered the most powerful telescope in history. It is not located on Earth, but in space, 1.5 million miles away from our planet, which gives it a great advantage in terms of quality. It is equipped with the most powerful cameras and lenses capable of capturing in different modes. The telescope captures part of the cosmos. They shoot it with dozens of different exposures, shutter speeds, and filters. All the footage is sent back to Earth and collected, and scientists reconstruct the big picture. They also color the pictures, because the pictures are originally black and white, but they do it for a reason. There is science and a strict set of rules behind every color and shade of the celestial glow. Now, look at these pictures. It may look like gold under a microscope or an impressionist painting, but it's the sun. Yes, that's our star. These pictures were taken recently and are the most recorded pictures of the sun. We can see the boiling plasma in great detail, but they're relatively small. Look at the scale. Here's a close-up of one of the images compared to Earth. In this area, the sun would be several tens of times larger than our Earth, and the smallest points would be 30 kilometers in diameter. These images were taken by the Inouye telescope. While James Webb specializes in galaxies, Inouye specializes in solar telescopes. Also, unlike its iron counterpart, it is located on Earth, on the Hawaiian island of Maui. It's amazing that we get such clear images of a celestial body 150 million kilometers away. You know what's even more amazing? Touch the sun directly. Fly as close to it as possible and take some of the most interesting pictures in the history of space. You think this is science fiction? No, it's been a reality for a long time now. It's hard to believe, but scientists have managed to create a unique material that can survive contact with the sun. A probe called Parker reached the sun in 2018, literally touched it, and studied the solar wind and other aspects of our star. It succeeded in 2021 when it crossed the boundary of the solar corona. Of course, it didn't land on the star itself, but it was very close to it on a cosmic scale, less than 9 million kilometers. In addition, the probe continues to work with the star and gets closer to it every year. By the end of this year, about 6 million kilometers should be passed. How has Parker not caught fire yet? It seems somewhat unrealistic, but it all makes sense. First of all, the tent is very sturdy and made of modern materials. It has a special carbon fiber heat shield that is 11 centimeters thick and several meters wide. In addition, all the equipment is surrounded by a radiator with water that is constantly circulating, drawing heat away from the hottest parts and continuously cooling. Considering that the surface temperature of the sun is about 5,000 to 6,000 degrees, the umbrella can withstand about 1,500 degrees of heat. And the tentacle doesn't get close. It can get close before it burns up. Agreed, 100 million years is a long time, and it's hard to predict what will happen after such a long period. So, to simplify, let's start with smaller periods. For example, in 100 years, the population growth trend is increasing. Those of you who are older will remember that at the beginning of the 21st century, the world population was about 6 billion. In 10 years, it has grown to 7 billion. And that's usually the number most of us call when we ask about aliens. At the same time, it has surpassed 8 billion and continues to grow. Scientists predict that in 100 years, there will be 10 to 11 billion people living on Earth. It's going to be a little more difficult, but that's beside the point. Humans continue to release carbon dioxide into the atmosphere and use technology to reduce humidity. All of this is heating up the planet even more, and glaciers don't like it. They are actively melting, and in 100 years the appearance of the Earth will change. Tuvalu, Kiribati, Nauru, these countries, as you just know, will disappear underwater. The same thing awaits other countries and places. For example, our grandchildren and great-grandchildren will not be able to retire in the Maldives, Tahiti, and the Bahamas. These legendary spas will also be underwater, and only SpongeBob and his friends will be able to enter them. The terrain will change slightly, but it will be easily recognizable from satellite imagery. Meanwhile, the continents will continue to move. True, they will not move very fast, and in a few centuries and millennia, the appearance of the Earth will remain the same, give or take, the same. Indeed, major changes will occur within millions of years. In about 100 million years, the Earth will look as if dinosaurs roamed it. It is thought that at that time the continents will merge again and hug each other tightly, creating a new Pangea. Some people think 100 million years will be enough time. Others say that a new supercontinent will appear in 200 million years at the earliest. As you can see, the seas are almost gone. The continents will stay in one place, and around them will be the great ocean of the world. Good news for future aerophobes. In 100 million years, it will be possible to get anywhere on Earth by car, if there was such a thing as an automobile at that time. It's true that not all scientists share this future scenario. Some believe that instead of a new Pangea, Pangea Proxima or Pangea Ultima has formed. The continents will also be joined together, but not as tightly. Inland seas and intercontinental waters would remain. Sorry, aerophobes, you'll still have to fly, but perhaps in the distant future, flying will be done on ultra-safe rockets. Or will mankind even master teleportation? Why not? Another option is the supercontinent of Amasia. It is called so because the base will be America and Asia. Aerophobes can breathe again. The supercontinent would merge into new Pangea. Of course, its center will be at the North Pole, so you'll have to isolate yourself. There's another scenario. There will be no supercontinent. The tectonic plates will continue to move. The Earth will lose its current shape and change, but it will still be the same as it is now. The boundaries and outlines of the continents will be blurred, and many areas will be flooded. In this scenario, in 100 million years, Canada will be left behind. Much of South America will be destroyed, and Africa and Europe will be significantly flooded. Japan and the Philippines may move to the Americas. Either Australia will go underwater, or it will move towards Eurasia, so that it will not be left alone. Over the next 100 million years, our planet's climate will change many times. First, as I said, global warming will increase, and the planet will be hot at first. If we advance significantly, in the future the Earth will change its tilt, making some places unrecognizable. For example, the Sahara will eventually stop being a dry hell and become a tropical paradise with dense jungles. Can you imagine that? Meanwhile, what will eventually become a jungle will turn into a grassy plain. That's the future for the Amazon rainforest. In addition, some other areas will be partially flooded. This is especially true for countries that are literally on the water, such as the Netherlands. But everything is cyclical. Global warming will lead to a new ice age. Scientists believe that this ice age could be the most global, severe, and brutal in the history of the planet. A large glacier several kilometers thick will cover most of the northern hemisphere of Europe, Siberia, and North America. Future screenwriters will have a great opportunity to recreate the Ice Age with new animals instead of Manny, Sid, and Diego. By the way, about animals we will talk soon. Did not do without cataclysm. So people of the distant future shouldn't be disappointed in a rare Earth or a renewed Sahara. Approximately every 50,000 years, the volcanic activity of the planet reaches a peak. So from time to time, the planet will be scorched by volcanoes and supervolcanoes. The same Yellowstone volcano will make itself known in the next 100 million years. but it could spread in the relatively near future. The consequences would be catastrophic. Severe cooling due to volcanic dust in the atmosphere, earthquakes, and ground faults. And all of this has some side effects that could cause serious rashes. I can't do without visitors from outer space. Over the next 100 million years, the Earth will be bombarded repeatedly by meteorites, comets, and asteroids. Some of them will be relatively harmless, but others will cause explosions so violent that their voices will be heard everywhere. Of course, all of this will cause unprecedented earthquakes and tsunamis of heights from the skyscrapers of New York and Dubai. At some point, bombardment from space will become the daily norm, as the movement of celestial bodies in the solar system and the impact of random stars approaching them will cause asteroids to collide with the planet at an insane frequency. Along with Earth, other planets will begin to undergo some changes. Saturn, for example. Its rings are slowly disappearing. Even now, some scientists are predicting the demise of Saturn's rings. Some say it will be next year. That's impossible, of course, but in tens of millions of years there will be nothing left of them. Saturn will lose its core identity. But what is even more interesting is not what will happen to Saturn, but what will happen to people on Earth, such as animals. Many well-known species will become extinct in the coming decades or even centuries, such as the Amur tiger, some leopards, polar bears, pandas, whales, bears, and even gorillas. Nothing truly global will happen in the short term, but if you look a few million years into the future, the fauna will be very different. All large mammals are predicted to die or shrink in size due to climate change and natural disasters. Good news for our distant generations. They will be able to tame the common hippo or buffalo and domesticate them. Well, that's impossible. Experts believe that within millions of years there will be no pets and no living pets. Perhaps the pets will be some robots, holograms, or something more amazing. As for living creatures, the distant future will be a period of flourishing of large amphibians and unusual mollusks, and in general, our planet will be home to terrible animals, which can now be imagined only in the imagination. So, according to predictions, palaces with giant tentacles will fly across the sky. They have not yet been given a name, but it is given to another animal, the swamp animal. Apparently, they will be octopuses, capable of living in the water for days, picking up large plants and land plants. Together with flying squirrels, they will be one of the most dominant animals in the world. Teratons and giant tortoises will also inhabit the planet. And even if not, what an abnormal and insane turtle, weighing 120 tons. Modern Galapagos tortoises look like ants in comparison. Speaking of ants, some scientists believe that ants may be one of the main hosts of the planet in the animal world. They appeared during the time of the dinosaurs. They successfully escaped from these terrible lizards and live perfectly well in our time. Ants are very intelligent, hardworking, and organized, and there are a lot of them. The total number of ants on the planet reaches 20 quadrillion. This is followed by 15 zeros, or 1,000,000 billion. They can easily survive any shocks and cataclysms and can rule the planet along with superhabs and creepy octopuses. Although the extinction of large mammals is predicted in the distant future, at the same time, some experts believe that there will be some new large animals that will not be able to adapt to the best conditions of the planet. For example, there will be a mix of giant antelope, deer, and antelope. There will also be furry pikemen that resemble hybrids of giraffes and elephants, and many other strange creatures. In addition, dangerous breeds of bugs, deadly creatures, will be found in the world of the far future. They must sleep at night and hunt during the day. In appearance, The killers resemble winged foxes. They will live in caves in large herds. And that's not all. According to some scientists, one of the most dangerous predators of the future is an unknown flying creature with a 2-meter wingspan and huge claws called Dagliner or Death Collector. The snowy north of Europe is home to a modern breed of ermine or wolf called the snow stalker. This snow hunter looks like a sablasuber, samaha, covered in thick, warm fur. These are not just octopuses coming out of the oceans. They will evolve into baby octopuses. Evolution doesn't stop, so some marine animals will leave the water and become land creatures. Scientists hypothesize that orcas and catfish will do just that. Colonies of large flying spiders will settle in the clouds, and birds caught in their webs, like modern monkeys, will begin to descend. All in all, in millions of years, the animal world will resemble some horror movie or dreams at 39 temperatures. The animals have been sorted out. Now the most important thing is what will happen to people. What will the people of the future look like? Let's get this straight. First, scientists predict an increase in brain size. There is a logic to this. Evolutionarily, our brains have gotten bigger. We evolved and became Homo sapiens. In 100 million years, the human brain will increase in size. Some experts say that 20 kilograms is a crazy amount. But how much will the gray matter of those distant humans weigh? This is probably an exaggeration, but many scientists have no doubt that the brain will be bigger. You will also have less hair on your head, which makes sense. If you look at ancient and primitive people, you will see that they have hair. Back then, their thick hair kept them warm from the cold, as there was no trace of heating batteries or warm apartments. Now that the heating problem has been solved, hair is becoming an increasingly unnecessary element. It is believed that in time, people will lose all their hair and grow eyebrows. Other unwanted body parts will also disappear. Wisdom teeth, tailbones, and nipples will likely disappear. The future person's nose will be much smaller. Some predict that the nose will disappear completely in our generation. So in the long run, several planets will be populated by Voldemorts. As humans get taller and taller over time, the humans of the future will be much taller. Perhaps 2, then 2.5, or even 3 meters tall will become the norm. Life expectancy will also increase. If we look ahead, we might think that humanity will achieve immortality, partially or even completely. Now, they are discussing the topic of transferring consciousness from the physical body to some virtual environment with the possibility of its subsequent transfer to another body. In particular, a person can be scanned, data recorded on a cool flash drive, and then implanted into a new, disease-free, young body. Sounds crazy, but futurists believe that such technologies could appear in the 21st century. What can we say about 100 million? By then, things may be more advanced, and this technology may even seem somewhat primitive to our distant generations. As for having children, in the distant future this could be done artificially, in special flasks and incubators. Women will no longer have to suffer nature. At the same time, some believe that such technology, if developed, could desexualize humanity. Finally, the future lies in cloning, bioprosthetics, implants, nanotechnology, bioengineering, genetic modification, etc., which allow us to enhance our skills and abilities. Will be very advanced. Perhaps millions of years from now, humans will not look like us at all. They will be like digital cyborgs with immortal consciousness and the ability to live in different bodies and on different planets for thousands of years. And it is predicted that in the distant future, people will learn to communicate with animals. It's clear that people of the future will actively use technology to work themselves, their bodies, and brains to the limit. But technology will permeate every aspect of life. Today's climate, disasters, etc. Given what you've heard about, it's hard to say whether humans will be able to live on Earth in 100 million years. But it is still possible for some people to live on Earth. Scientists believe that there are still a few billion years left before our planet dies, and 250 Earths will only be alive in 250 million years. Consequently, humans in the distant future will somehow be able to settle on Nova Pangaea or Pangaea Proxima. Of course, our available resources will be exhausted faster than 100 million years. Consequently, to live on the planet, we will have to take advantage of space. Programs are being developed to launch asteroid debris, and it is likely that in the distant future, asteroid missions to Earth will become permanent. In the meantime, future technology will allow them to synthesize food, and perhaps they will drink water on an industrial scale to solve the problem of hunger. Due to flooding of many parts of the planet, people living on Earth will move to the most comfortable places and take care of protection from meteorites, asteroids, volcanoes, and other problems. In 100 million years, technology will have developed so much that future cyborgs will be able to build some kind of protective shield over the surviving parts of the planet. And, of course, space travel will become commonplace. Although the first flight to Mars is planned for the near future, in a couple hundred years, the red planet could be colonized. What to speak of millions of years? Due to overpopulation and problems, mankind will not be able to fully live on Earth. Many will move not only to Mars, but also to other planets outside the solar system. In the future, technology will undoubtedly allow rapid travel from one system to another. Therefore, traveling to a friend from another planet may become an everyday reality. If all goes well, humanity will no longer be in the billions, but trillions or even quadrillions of cyborgs. It is likely that humans will spread across galaxies, and the achievements we are proud of now will seem meaningless and pointless to the people of the future. Everyone would like to believe that this is the case, but it's all speculation. As I said at the beginning of this issue, 100 million years is a very long time, so it is impossible to say exactly what will happen after such a long period of time. That said, it is important to remember that significant changes could begin to take place in our immediate future. We must take care of the Earth and knowledge now, and try not to destroy ourselves so that our distant generations can live happily on other planets. The observable universe is home to truly astonishing large-scale structures that represent the breadth and depth of cosmic architecture. Among these giants are galaxy superclusters, large groups of galaxies that are gravitationally bound together. One of the most prominent superclusters is the Laniakea supercluster, which serves as our cosmic neighborhood. It contains approximately 100,000 galaxies and spans over 150 million light-years, representing the mind-boggling scale involved in our universe. In addition to superclusters, there are even larger formations known as cosmic filaments. These filaments consist of galaxies and dark matter, weaving complex patterns into the large-scale structure of the universe. The Sloan Great Wall is an important example of a cosmic filament, more than 100 million light-years long. Such large structures are interconnected to form a vast web architecture with empty spaces between them. This suggests that galaxies are not evenly distributed throughout the universe, but rather they form a complex region under the influence of gravity and dark matter. Even more impressive are the largest structures ever discovered, such as the Great Wall of Hercules Corona Borealis. This massive supercluster measures about 10 billion light-years across and is considered the most well-known structure in the observable universe. Its discovery complicates our understanding of cosmic evolution because it raises questions about how such large regions come together and what forces govern them. These massive structures provide important insights not only into the vast scale of space, but also into the fundamental processes that shape the universe over billions of years. As scientists continue to study them, they learn more about the basic fabric of matter, energy, and nature. The pursuit of knowledge about these great clusters piques our interest and our desire to understand our place in this grand cosmic scheme. Galaxy filaments and cosmic networks are the result of gravitational interactions and the complex dynamics of dark matter in the universe. These structures appeared in the early stages of cosmic evolution, after the Big Bang. As the universe cooled, matter began to clump together under the influence of gravity. Dark matter plays a key role in this process. It does not interact with light, making it invisible, but its gravitational pull has a significant effect on the distribution of galaxies. Over billions of years, regions with a slightly higher density of core matter began to attract more matter, forming the seeds of galaxies and clusters. As these local gravity wells deepened, they attracted more and more material from their surroundings. This created filaments, which are long structures that look like spaceships. These filaments connect large clusters of galaxies and form the web structure that fills the universe. As the universe continues to expand, the dynamics of matter evolves. Galaxies within the filaments are attracted to each other, eventually forming clusters at their intersections. This gravitational hierarchy is surrounded by high-density large voids that contain relatively few galaxies. The interplay of filaments provides the foundation upon which the universe is structured, displaying a beautifully orchestrated spatial arrangement. Computer simulations and observational data from telescopes are further enhancing our understanding of this phenomenon. These simulations show how dark matter affects the evolution of cosmic structure. Large-scale surveys, such as the Sloan Digital Sky Survey, allow astronomers to detect and map these large filaments, confirming theoretical models. Together, they reveal the dynamic processes that create the elegant cosmic web that spans our universe. Cosmic voids are the vast, empty spaces between galaxies and galaxy clusters that represent some of the larger structures in the universe. These voids can be tens to hundreds of millions of light-years across and are characterized by a lack of matter compared to denser regions. Although they appear to be devoid of galaxies, a closer inspection reveals that they are not entirely empty. They often contain faint galaxies, dark matter, and diffuse gas, albeit in much lower concentrations than their denser counterparts. The existence of these cosmic voids provides insight into the overall structure of the universe. The proliferation of voids and their surrounding filaments and clusters represent the web-like architecture of the universe, a phenomenon that reflects the influence of gravity over billions of years. Gaps are crucial to understanding cosmological evolution because they help scientists investigate the origin and nature of cosmic structure. By studying the vacuum, researchers can understand the changes in density that occurred in the early universe. Moreover, the properties of cosmic voids challenge our understanding of dark energy, the mysterious force that causes the universe to accelerate. The behavior of matter in and around voids can reveal valuable information about how dark energy affects the expansion of space. For example, observing how galaxies move in and around voids can provide information about the distribution of mass in the universe and help us understand cosmic dynamics. The study of cosmic voids also raises interesting questions about the fundamental nature of the universe. They serve as testing grounds for cosmological models, allowing researchers to assess the validity of theories such as the Standard Model of cosmology. As science advances and observational techniques improve, space probes continue to unravel the mysteries of the universe, enhancing our understanding of the governorship of cosmic evolution. Dark matter plays an important role in the formation and evolution of cosmic structures throughout the universe. Although invisible, neither emitting nor absorbing light, dark matter makes up about 27% of the total mass-energy content of the universe. Its gravitational influence is key to understanding how galaxies, clusters, and even larger structures such as superclusters and cosmic filaments are formed and maintained. In the early universe, after the Big Bang, matter began to clump together under the force of gravity. Although the normal matter that emits light and forms stars and galaxies begins to accumulate, it is dark matter that does not appear to form the basis of this cluster. Dark matter does not interact electromagnetically, meaning it does not collide with matter to dissipate energy. This property allows it to remain gravitationally bound and form massive halos surrounding galaxies and clusters. These halos act as gravitational wells, attracting ordinary matter and helping the formation of stars, galaxies, and larger structures. The processes of cosmic evolution and structure formation are closely related to the behavior of dark matter. When galaxies merge or interact, their dark matter can also collide and merge, which can lead to the growth of large galaxies and galaxy clusters. Understanding the dynamics of dark matter interactions helps scientists explain phenomena such as the rotation curves of galaxies. These curves show that stars orbiting outside galaxies are moving faster than expected based on visible matter. This suggests that there is additional invisible mass associated with dark matter. Astronomical observations and simulations of large-scale structures shed more light on the role of dark matter. By mapping the distribution of galaxies and clusters, researchers can map the corresponding distribution of dark matter. Projects such as gravitational lensing provide direct evidence of the existence and distribution of dark matter throughout the universe by measuring how light from distant objects is bent by massive structures. As researchers continue to explore the nature of dark matter, they enhance our understanding of its profound effects on the cosmic landscape and the structure of our universe. Beyond our observable universe lies a tantalizing and enigmatic realm. Although we can analyze the structures in the cosmic environment, understanding the nature of these cosmic structures is influenced by many different cosmological theories. One common idea is that the conditions surrounding these structures may vary, resulting in different formations. For example, while our universe exhibits a specific distribution of galaxies, clusters, and voids, other regions may vary in density and order, resulting in different large-scale structures. One hypothesis suggests that physical laws may differ in different regions of the universe. If fundamental constants such as gravity or the speed of light differ from our observable horizon, the evolution of cosmic structures in these regions may produce results that differ dramatically from what we witness nearby. Such changes could lead to exotic astrophysical entities or entirely new celestial shapes that defy our current understanding of physics. In addition to potential changes in physical laws, the overall geometry of spacetime is a critical factor influencing the structure of the universe. Measurements of the cosmic microwave background radiation suggest that the observable universe appears to be flat. However, if the universe is truly infinite and far beyond what we can observe, it could introduce various curvature features that could affect the development of large-scale cosmic structures. The concept of the multiverse also comes into play, where our universe is potentially one of countless others, each with its own unique physical properties and structural formation processes. In such a scenario, some universes may adopt strange structures or even strange rules governing their cosmic evolution. While these ideas remain speculative, they drive the imaginations of scientists and theorists, furthering the exploration of the mysteries of the universe. Attempting to understand these hypothetical cosmic realms beyond the visible universe deepens our uncertainty. Dark matter is a mysterious, non-luminous component of the universe that does not emit, absorb, or reflect light, making it invisible to conventional observational techniques. Dark matter is thought to make up about 27% of the mass energy of the universe. Scientists estimate its existence based on its effects on visible matter, radiation, and the overall structure of the universe. One of the strongest lines of evidence for dark matter comes from observations of galaxy rotation curves. When astronomers measure the speed of stars orbiting in the outer regions of galaxies, these stars move much faster than expected based on the gravitational effects of visible matter such as stars and gas. According to Newtonian physics, they should show a decreasing velocity as they move away from the galactic center. However, the observed velocity remains constant, indicating that the galactic halo contains more mass than can be accounted for by stars and gas alone, possibly in the form of dark matter. Another important piece of evidence comes from gravitational lensing, the phenomenon in which light from distant galaxies is bent by the gravitational pull of large foregrounds such as galaxy clusters. Observations show that the amount of bending goes beyond that which depends only on the apparent mass. This inconsistency suggests that there is additional invisible mass that exhibits gravitational pull, consistent with the presence of dark matter. Moreover, the distribution of galaxies in the universe follows a web structure under the influence of dark matter. Cosmic structure formation simulations involving dark matter agree closely with observations of the large-scale structure of the universe, such as galaxy clusters and voids. These models suggest that dark matter acts as clusters of visible matter that guide the formation of galaxies and other cosmic structures. The exact nature of dark matter remains a deep mystery, and various candidates have been proposed, such as non-massive particles. Research is ongoing, using cutting-edge technologies and experiments aimed at directly or indirectly detecting dark matter. The search for dark matter is important because it not only holds the key to understanding the composition of the universe, but also informs the fundamental laws that govern the cosmos. Dark matter has a profound effect on galaxy formation and the overall architecture of the universe. Its gravitational properties are important in shaping the large-scale structure we observe in the universe today. In the early universe, shortly after the Big Bang, dark matter began to clump together, forming massive halos that provided a gravitational field within which ordinary matter could gather. This high concentration of dark matter created gravity wells that attracted gas, dust, and other simple matter, facilitating the birth of galaxies. As galaxies form, their dark matter plays an important role in determining their size, mass, and rotation speed. Dark matter helps maintain the stability of galaxies by providing additional gravitational pull only with visible matter. This stability is particularly important because the forces at play during galaxy formation are enormous, and the gravitational pull of dark matter allows complex structures to form that do not collapse under their own dynamics. When galaxies interact or merge, the dynamics of their dark matter has a significant impact on the outcome of these events. For example, during a merger between two galaxies, their dark matter halos can collide and merge with visible matter. This interaction can lead to the formation of larger galaxies, which often exhibit different properties compared to smaller ones. This merger process is a critical aspect of galaxy evolution, contributing to the development of cosmic structures throughout the universe. On a larger scale, dark matter represents the overall distribution and motion of galaxies. The gravitational influence of dark matter creates the structure of the cosmic web, where galaxies and clusters form along filaments and nodes with large gaps between them. This gravitational network shows how dark matter organizes space and affects the motion of galaxies over time, shaping the dynamic behavior of galaxies and clusters as they move through the evolving universe. Dark matter is more than just a facilitator of cosmic evolution. It serves as the primary force driving the formation and construction of galaxies and the larger cosmos. The search for dark matter particles has led scientists to propose several interesting candidates, each from a different theoretical background in particle physics and cosmology. One of the most widely studied candidates is the weakly interacting massive particle, often abbreviated as WIMP. WIMPs are predicted to have masses on the order of hundreds of GeV or giga-electron volts and interact with the weak nuclear force and gravity. The theory postulates that they were produced in large quantities in the early moments after the Big Bang. Direct detection of WIMPs will be difficult due to their weak interactions, but some experiments aim to observe scattering events with potential matter. Another promising category of dark matter candidates is the hypothetical elementary particle proposed to solve problems related to quantum chromodynamics. Particles are light, slow-moving particles that can make up a large portion of dark matter. They will interact very weakly with other particles, effectively repelling them. Researchers are exploring the potential for detecting axons through experiments that look for them to convert into photons when exposed to strong magnetic fields. There are also supersymmetric particles, which arise from theories that extend the standard model of particle physics. In these models, each elementary particle has different properties. Candidates from supersymmetry, such as neutralinos, have the necessary properties to account for dark matter. Their stability and interactions governed by the weak force make them strong candidates in some theoretical frameworks. Finally, supermassive black holes provide an alternative explanation for dark matter. These would arise from changes in density in the larger universe, potentially accounting for the effects of dark matter through gravitational interactions. Although this theory differs from ordinary particle candidates, it remains a point of active research given the complexity of cosmological evolution. These candidates bring together the various approaches taken to solve the dark matter enigma. Ongoing experiments are designed to detect or rule out these possibilities, improving our understanding not only of dark matter, but of the fundamental physics of the universe. Each approach promises to advance scientific knowledge and may lead to profound discoveries about the composition of the universe and the laws that govern it. Dark energy is an enigmatic form of energy that permeates all of space and is responsible for the observed acceleration of the universe. Dark energy, which accounts for about 73% of the total mass energy content of the universe, has puzzled scientists since its discovery. Unlike ordinary matter and dark matter, which are gravitationally attracted, dark energy exerts a repulsive force, causing galaxies to accelerate apart from each other. Traces of dark energy were first discovered in the late 20th century, primarily through observations of distant supernovae. In the mid-1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure the luminosity of Ja supernovae, which serve as a reliable standard candle for determining cosmic distances. By observing these supernovae, teams would discover that the universe's expansion is slowing due to gravity. However, their data showed a surprising result. The supernova appeared darker than expected, indicating that they were farther away than previously thought. This led researchers to conclude that the expansion of the universe is accelerating rather than slowing down. The key to understanding this acceleration lies in the concept of dark energy. To explain the observations, scientists introduced dark energy as the driving force behind the accelerated expansion. Various theoretical frameworks have been proposed to describe dark energy, one of the most famous models of the cosmological constant. The cosmological constant, proposed by Albert Einstein at the beginning of the 20th century, simultaneously complements the energy density. This reflects the idea that as the universe expands, the energy density remains constant. Other theories have emerged, including quintessence, which suggests that the density of dark energy may change over time. Despite these various models, the true nature of dark energy remains elusive. Observations of the cosmic microwave background, the large-scale structure of the universe, and other astrophysical phenomena have helped improve our understanding of dark energy. Ongoing research continues to investigate this mysterious substance, as unraveling its nature could shed light on fundamental aspects of the universe and the ultimate fate of cosmic evolution. Dark energy plays an important role in the future of the universe, primarily because of its role in the accelerated expansion observed over the past few billion years. As dark energy continues to exert its influence, it shapes potential scenarios for the ultimate fate of the universe. The exact nature of dark energy remains an open question, but its consistency suggests several futures for the universe. Big Freeze Scenario. In this model, as the universe expands at a rate controlled by dark energy, galaxies gradually fade away from our observable horizon. Over large timescales, star formation will slow down, leading to an increasingly cold and dark growing universe. Existing stars will run out of nuclear fuel, and without new stars forming, most of the matter will remain in the form of black holes and white dwarfs. Eventually, the universe will reach a state of thermodynamic equilibrium, characterized by a uniform temperature near absolute zero, rendering it a desert and inert space. Another scenario is a big rip, where the influence of dark energy increases, causing the escape to expand. In this model, the accelerated expansion can be so pronounced that it eventually separates galaxies, stars, and even atoms. If the energy density of dark energy increases without limit, all large-scale structures will collapse, ultimately leading to a catastrophic end to the universe. At the other end of the spectrum, some theories suggest that dark energy could evolve over time, perhaps leading to a steady state or even transitioning to gravitational forces. This change could reverse the current acceleration of cosmic expansion, allowing galaxies to merge and form larger structures, leading to a cyclical pattern of cosmic evolution. As researchers gather more information from observations of supernovae, the cosmic microwave background radiation, and galactic scattering, they aim to improve our understanding of dark energy and its effects on the universe. Each of these potential destinies points to the complex relationship between dark energy and the cosmos, revealing how this mysterious force can ultimately shape evolution and the fate of everything within it. The evidence for the expansion of the universe is strong and multifaceted, contributing to our understanding of cosmological dynamics. One of the earliest and most compelling evidences comes from observations of galaxies and their redshifts, recognized by Edwin Hubble in the late 1920s. Hubble noted that distant galaxies are moving away from us, and the light they emit shows a shift to the red end of the spectrum. This red shift indicates that the wavelengths of light are stretched as galaxies shrink, a phenomenon consistent with the Doppler effect. Hubble formulated his law, which states that the farther away a galaxy is, the faster it is moving away and the universe is expanding. In addition, the cosmic microwave background rays, the glow left over from the Big Bang, provide further support for this expansion. Discovered in the 1960s, this relic radiation is remarkably uniform, but there are small variations that reveal information about the density and temperature of the universe. Measurements from satellites, such as the Wilkinson Microwave Anisotropic Probe and the Planck mission, show these changes with great precision. According to the data, the universe has been expanding since its creation, and the cosmic microwave background serves as a snapshot of the universe as it was around 300,000 years ago, after it cooled enough to form atoms. Supernovae also contribute to the evidence for the universal expansion, particularly type Ia supernovae, which serve as reliable standard candles for measuring astronomical distances. Observations at the end of the 20th century showed that these supernovae were less luminous than expected, suggesting that they were far away due to the acceleration of the universe's expansion. This discovery was instrumental in proving not only the expansion of the universe, but the expansion rate is increasing due to dark energy. Finally, the large-scale structure of the universe, including the distribution of galaxies and cosmic filaments, provides additional evidence for expansion. Current observations show that galaxies are not uniformly distributed. Instead, they form a large cosmic web structure that interacts with gravity. This distribution is a direct result of the expansion history of the universe, further reinforcing the paradigm of a dynamically evolving cosmos under the influence of forces at play since the Big Bang. Together, this evidence creates a powerful picture of an ever-expanding universe, with each piece contributing to our understanding of its origins and evolution over time. The Hubble constant is a key parameter that describes the rate at which the universe is expanding. It shows the relationship between a galaxy's distance and its rate of recession, providing a measure of how quickly galaxies are moving away from us as the universe expands. The Hubble constant is usually expressed in megaparsecs per kilometer per second. meaning that for every additional megaparsec, the galaxy is receding by a certain number per second. Edwin Hubble's discovery of this relationship in the late 1920s fundamentally changed our understanding of the universe. His observations showed that galaxies farther from Earth are receding at a greater rate, indicating that the universe itself is expanding in one direction. This expansion can be thought of as the stretching of space, with the galaxies embedded in that space dissipating over time. Understanding the Hubble constant is critical to determining the size and age of the universe. By measuring the recession velocities of different galaxies and their distances using methods such as standard candlestick or redshift measurements, astronomers can calculate the Hubble constant. This measurement allows scientists to estimate how long the universe has been expanding since the Big Bang, yielding its age, which is currently about 13.8 billion years. However, it should be noted that measurements of the Hubble constant yielded slightly different values depending on the methods used. Planck satellite observations measuring the cosmic microwave background radiation suggest a certain value for the Hubble constant, while measurements from large surveys of supernovae and galaxy distributions provide larger values. This discrepancy has led to debate and research in the field of cosmology, as scientists seek to reconcile these differences and better understand the underlying physics of the universe's expansion. Ultimately, Hubble serves as an important bridge connecting observations of constant recession velocities and distances, strengthening its role in understanding the expanding universe and guiding future investigations into its fate. Cosmic acceleration refers to the observed expansion of the universe over the past few billion years. This continuum behavior indicates that the galaxies are moving away from each other at increasing speeds rather than slowing down, as would be expected from gravitational acceleration. The discovery of cosmic acceleration changed our understanding of the dynamics of the universe and had important implications for cosmology. The main explanation for cosmic acceleration is dark energy, a mysterious form of energy that permeates space and resists gravity. Dark energy is thought to make up 73% of the total energy density of the universe. Unlike ordinary matter, which has a gravitational pull, dark energy appears to be a repulsive effect pulling galaxies apart. The nature of dark energy remains one of the most profound enigmas of modern astrophysics, with various theories proposed to describe its properties, including the cosmological constant, which is a constant energy density. Observations supporting cosmic acceleration come primarily from studies of distant supernovae, particularly type Ia supernovae. These supernovae serve as reliable distance indicators, allowing astronomers to measure the expansion history of the universe. When the researchers found that these supernovae were weaker than expected, it showed that they were farther away than previously thought, leading to the conclusion that the expansion of the universe is accelerating rather than accelerating. Another piece of evidence for cosmic acceleration is observations of the cosmic microwave background radiation and large-scale structure. Measurements of changes in the cosmic microwave background after the Big Bang provide insight into the density and composition of the early universe. The subsequent spread of galaxies and galaxy clusters through space is consistent with an accelerated expansion scenario, as structures formed from density fluctuations are influenced by dark energy. Despite extensive research on dark energy and cosmic acceleration, questions remain about its true nature and behavior. Ongoing experiments and observational campaigns aim to improve our understanding, potentially revealing physics and changing our understanding of the evolution and fate of the universe. The implications of cosmic acceleration and dark energy are not only interesting, but also delve into deeper questions about the very fabric of reality. The expansion of the universe is of great importance not only for the regions we can observe, but also for the regions beyond the observable limits. As the universe expands, it affects the dynamics and distribution of matter on large scales, and this expansion drives the evolution of cosmic structures both within our observable universe and in regions beyond it. One of the main effects of this expansion is the notion that the regions beyond our observable universe may be shrinking away from us at speeds exceeding the speed of light due to the metric expansion of space. This means that light from galaxies in these distant regions can never reach us, remaining forever beyond our cosmic horizon. As the universe continues to expand, many of these regions will move away from our observables, leading into the future, when the night sky will slowly empty of distant galaxies. This eventual isolation can lead to a universe that appears dark and desolate, changing our perception of space over cosmological timescales. Magnification effects raise interesting questions about the potential existence of structures beyond our observable universe. While we cannot directly observe these regions, theoretical models suggest that they may contain galaxies, clusters, and cosmic filaments similar to our observable limits. However, these structures evolve differently depending on local conditions, gravitational interactions, and dark energy distribution. Such changes may mean that the universe we see is not just an extension of what we can observe, but may offer unique features. In addition, the rate of expansion can affect the fate of the universe. If the properties of the dark model change, as some models suggest, this could lead to very different cosmic scenarios in the observable and unobservable regions of the universe. For example, if dark energy becomes stronger, it could lead to Big Rip-like scenarios where cosmic structures are disrupted, even affecting the integrity of the farthest reaches of space. Ultimately, as scientists continue to study the fundamental laws governing the expansion of the universe, our understanding of its consequences will be near and far. Uncharted regions of the universe may hold secrets that defy our understanding and help us understand the fabric of reality, even if we never see it with our own eyes. The ultimate fate of the universe is a topic of great intrigue among cosmologists, with prevailing theories suggesting several potential scenarios based on the expansion of the universe and the nature of dark energy. As the universe continues to expand, it will push galaxies further apart. This expansion, driven by dark energy, is accelerating over time, leading to the possibility of a superfreeze. In this scenario, the universe becomes increasingly cold and desolate. Stars run out of fuel and galaxies recede until they fall into obscurity. Alternatively, some models predict a major collision. In this scenario, if the universe is dense enough, gravity can eventually stop expanding. The universe would then collapse back under its own gravity, potentially creating a singular state similar to the conditions at the beginning of the universe. This collapse could return all matter to an infinitely dense point, possibly leading to another Big Bang and the birth of a new universe. Another interesting possibility is the Great Rip. This theory suggests that if dark energy becomes stronger, it can tear apart galaxies, stars, planets, and even atoms. In this case, the fabric of the universe would eventually rupture, causing all structures to collapse violently. Finally, there is the concept of a steady-state universe, in which the expansion continues indefinitely, but the universe does not change over time, filled with new matter continuously created to fill the voids left by the expanding universe. These theories highlight the complexity and uncertainty surrounding the fate of our universe, calling for further exploration and research in the field of cosmology. 175,000 light-years away in the southern hemisphere's night sky in the constellation Golden Fish is a truly massive object. NGC 2070 is an emission embolus, better known as Tarantu. This tomb is gigantic and is believed to be the largest tomb known to date. This image shows one of the brightest space objects observed by Earth. To this day, there is no astronomer who has not heard of this cosmic miracle. The Tarantula Nebula is now the birthplace of stars. Earlier, behind the same powerful observational equipment, it was thought to be one of the brightest stars in the night sky, ahead of the constellation Goldfish. Nicolas Louis de L'Aquila was the first to recognize his true nature in 1751. Also, recent observations with modern telescopes have shown that this cosmic object is not a star at all, but rather a star in the sky. The size of this space object is huge. Imagine that this dome is about 1,000 light-years in diameter, If the closest object to us were replaced by the Orion Nebula, it would cover a third of the night sky. It would be 60 times larger than our familiar moon. He couldn't tear himself away from such a picture of the night sky. This dome overlooks the Milky Way's companion galaxy, the Large Magellanic Cloud. This emission is a large region of ionized hydrogen from which new stars form. Sources of ionizing photons are young, massive stars. Large dwarf stars are also powerful sources of radiation, producing large cosmic dusts of interstellar gas and dust. This is a very interesting phenomenon. These objects are formed by the gravitational influence of Tumbula's giant stars. Under this influence, gases explode, thus forming bulk-like shapes. Some stars explode in supernovae, most of which are illuminated by X-rays. That's why the Stellantis Nebula is so bright that we can observe it with the naked eye. Of course, for this you need to go to the southern hemisphere, and to see the exact outline of this space object as well as to see some of its great details, it is better to bring a good home or semi-professional telescope. But the VLT Survey telescope at the European Southern Observatory in Chile was able to capture this dwarf and its rich stars in great detail. Here, for example, you can see the cosmic landscape of various star clusters, glowing gas clouds, and scattered debris from supernova explosions. Tarantula Nebula is named after its resemblance to the venomous spider tarantula. Its central part is similar to its body and contains large and bright stars. The spider's legs are clusters of gases, mostly hydrogen. The region itself is filled with this chemical element, but this giant spider is really kind. Tarantula's legs hug one of the largest cosmic objects known to us, the star cluster NGC 2070, an active star-forming region, and at its dense center, R136 contains one of the largest and brightest stars. With the Hubble Space Telescope's unique ability to capture ultraviolet light, researchers have been able to detect monster stars in the R136 star cluster that are 100 times more massive than the Sun. It automatically studies the largest collection of stars we know of. This cluster was first known to contain massive stars 50 times more massive than the Sun, and a new study found that R136 contains at least 9 stars with a mass 100 times that of the Sun. Notable among them is R136A1, the current record holder for a massive star, which is 250 times more massive than the Sun and is considered the heaviest star in the known universe. Not only are the stars very massive, they are also very bright, about 30 million times the luminosity of the Sun. Astronomers were also able to study the emission of matter from these animals in the ultraviolet range. Over the course of a month, they emitted a mass comparable to that of Earth, which is 1% of the speed of light. With such parameters, it is believed that the flow of matter leads to a very rapid mass loss. Astronomers are still trying to explain the origin of such giant stars. These giant stars are thought to have formed from the merger of less massive stars in smaller binary systems. This cluster contains another interesting star cluster called Hodge 301, where at least 40 stars have exploded as supernovae, spreading envelopes of gas across the region. One example of a supernova remnant is a star cluster known as SNRN 157b, which contains the scattered star cluster NGC 2060. The cluster was discovered by British astronomer John Herschel in 1836, using an 18-inch reflector telescope at the Cape of Good Hope in South Africa. Outside the Tarantula Nebula, the famous supernova SN 1987A can be seen in its lower right region. A supernova was the first star observed by modern telescopes since Kepler's observations in 1604. SN 1987A's light was so intense that within months of its discovery in 1987, it emitted 100 million solar powers. But if you look to the left of this image, you can see another diffuse star cluster called NGC 2100, which shows us a collection of blue stars surrounded by red stars. This group was discovered by Scottish astronomer James Dunlop in 1826 while working with a 23-centimeter reflector in Australia. The nebula also contains the star cluster and emission Embolus NGC 2074, another large star-forming region. If you look closely, you can see a dark, dusty structure in the shape of a seahorse. This feature is called the Seahorse in the Large Magellanic Cloud. It's actually a long columnar structure 20 light-years across, which is almost 5 times the distance from our Sun to the nearest star, Alpha Centauri. This cosmic seahorse should disappear completely within the next million years as more stars form in the cluster, which will slowly sweep away these structures with radiation and winds. Yes, the Tarantulus Nebula is special. It is huge and contains many interesting things. It serves as a cradle for the birth of new stars, and at the same time other stars end their lives in supernova explosions. This is a wealth of information, and invaluable information for astronomers. What would happen if a supernova exploded near Earth? There are actually 3 answers, none of them very comforting. But before we answer them, let's try to understand what a supernova birth is and why, even if they are very distant, they can harm all life. Thus, a supernova star or supernova flare is a star that rapidly increases its luminosity, followed by a relatively slow decay. A supernova is observed post facto, that is, after the event and its radiation reaches our eyes. A supernova occurs when there is a change in the center or core of a star. The change can take 2 forms, and both lead to a supernova. The first type of supernova occurs in a binary star system. A binary star is 2 stars orbiting the same point. One of the stars, White 4, steals matter from its companion star. Eventually, the white dwarf accumulates an inappropriate amount of matter, and too much matter causes the star to explode. This is how a supernova is formed. The second type of supernova occurs at the end of a star's life. When a star runs out of nuclear fuel, part of its mass falls to the core. Eventually, the core becomes so heavy that it cannot resist its own gravity. The core collapses, causing a supernova star to explode. A powerful supernova explosion is the final stage of evolution, resulting in the formation of a new astronomical body, neutron star, or black hole in the universe. What kind of object a supernova transforms into depends on how the next stage of evolution proceeds. If the gravitational collapse is stopped by the internal pressure, a neutron star forms. Such stars are compact, with a radius of no more than 10 kilometers, a high density of up to 1 billion tons per cubic centimeter, and 2.5 times the mass of the Sun. After a supernova explosion, 2 types of neutron stars remain, pulsars and magnetars. The former is 10 times heavier than the Sun, and the latter is 40 times heavier. Pulsars rotate on their axis at high speed, creating an energy field, and the poles emit pulses of radiation. The strength of the magnetar's magnetic field is 50 trillion times stronger than that surrounding the Earth. If the mass of the supernova exceeds the mass of the Sun by a factor of 40, there is a 100% chance that the supernova formed after the star exploded. Black holes form as a result of gravitational collapse. When a supernova has a mass of 100 times the mass of the Sun or more, the probability of such an outcome is very high. Black holes attract an incredibly large amount of particles every second, quantities comparable to millions of Earth masses. Excess energy is emitted back into space as radiation. Such is the future of our nearest stars. Yes, it's a Betelgeuse star, 20 times more massive than our Sun. It is now in the red giant stage, albeit a long-term dead stage. Betelgeuse is one of the brightest stars in the sky. The red dot in the constellation. Orion continues to amaze with its mysterious behavior. At the end of 2020 it faded, but now it is back and has become 50% brighter in a few weeks. This is what led to rumors that Betelgeuse would explode. It's not hundreds of years, it's decades or even years. Eventually, when the star runs out of fuel, it will collapse under gravity and go supernova. What if Betelgeuse explodes now? Should we pack our bags and gear and grab a bloody guinea pig for the bunker? Yes, sometimes people start doing something when it's too late, and it's better to prepare everything in advance when the last star leaves the station. But how to find, what, and how to prepare? because our life is full of surprises. So if it's ethyl juice, we shouldn't expect much danger. Yes, it would be wonderful, but the earth would not be struck by a shock wave. The towers of heaven would not fall like matchsticks. The sea would not rise like a wall, and the inhabitants of the earth would not burn like the last day. Apocalypse. I'm sorry, Thanos. So what will we see? According to calculations, it should be the second supernova explosion. This means that Betelgeuse, to an observer in its own system, will briefly be 500 million times brighter than our Sun. Yes, indeed, it is blindingly bright. But of course we don't roll Betelgeuse. How bright will Betelgeuse be for us? Given the distance from Earth to the giant, calculations show that Betelgeuse will be about half as bright as the Moon. Betelgeuse will be visible both during the day and at night, but it will not be like the second Sun. During the day, Betelgeuse will appear as a large bright spot, larger than an ordinary star but smaller than the Sun. At night, Betelgeuse will appear as a large bright cloud, comparable in brightness to the Moon. Over the coming months, Betelgeuse will begin to fade, but will remain visible during the day for 6 months or up to a year. For another 2 years it can be observed with the naked eye in the night sky. Only then will it disappear. Unfortunately, not a single dome is visible around an exploding supernova at a time. That's a long time, so we'll have to wait a few more years before we see a spectacular dome around a once-dead star. Astronomers with their powerful telescopes will be able to see the star's outer shell sooner. Fact, the big boss in Betelgeuse is 642 light-years from Earth, so its supernova maximum will shower our planet with massless particles called neutrinos. Fortunately, they cannot harm us, because neutrinos are strange particles that have nothing to do with the world. Look at your right leg. Trillions of neutrinos from the Sun pass through it every second. You don't see this shower because neutrinos have almost no effect on ordinary matter. Every few years, on average, one neutrino from these snowflakes will pull away a poorly anchored atom in your body. History shows that at least a dozen supernova flares in the distant past have survived us unscathed, and some were not far from us. Researchers have even been able to study the effects of these fires, not because it's scary, but because it's fun. Yes, there are some effects. In particular, geological layers of the Earth corresponding to specific time periods contain concentrations of rare isotopes that could only be produced by gamma radiation. However, the number of these isotopes is limited to a few atoms per ton of matter. No one would have found him unless he looked as special as Indiana Jones. To this we can add the increased concentration of nitrous oxide in the Antarctic ice. By the way, far from serious science, publications appear in the press about the possibility of the extinction of dinosaurs due to a nearby supernova. Alas, they have no scientific basis, since there are no traces of supernova explosions in several million years and in dinosaur bones. But those supernovae were far away, so we're still here. What would happen if a supernova occurred in the near future? To begin with, it is good to understand what is close and what is far on the interstellar scale. Our nearest star, Proxima Centauri, is 100 times dimmer than the red Derby Sun. It's about 4 light-years away, and in any case, this star doesn't threaten us with a supernova, no matter how angry you are. The components of the same system are located a little further away, and stars such as Alpha, Centauri, and our Sun will not be able to complete their evolution in such a spectacular way. We had to look for heavy stars, but none of the ones around the Sun. Even the bright Procyon Alpha Minor is 1.5 times larger than the Sun. We are interested in stars 8 solar masses and heavier. They end the evolution with a celebration and fireworks. And one. In front of you is the double star IR Pegasus, located 150 light-years away, which is 4 times closer than Betelgeuse. None of the stars in this system can produce a supernova flash, but working together it can. IK. One of the stars in the Pegasus system is the white dwarf. The other has reached the stage of becoming a red giant. Over time, the evil dwarf begins to attach the upper layers of the giant to itself, increasing its mass. After reaching a certain mass, the white dwarf has a chance to go supernova. and they should take advantage of it. But by then the IK Pegasus system will be at a safe distance away from the Sun rapidly. However, if it happened now, it wouldn't be long before we felt its effects. One day we will see lights comparable to the Sun in the sky. For the Sun and the supernova to be on opposite sides of the Earth, the planet may not have any nights for a month or two. The visible light and heat rays from the supernova will cause a significant rise in temperature on the planet, albeit temporarily, and the radiation background would increase several times, which would put each Earth in a long mission to the ISS under astronaut conditions. But still, the inhabitants of our planet will be protected from the direct radiation of the supernova. For a while, earthworms will avoid bright light, stay indoors and play Tetris, go outdoors only when necessary, and cover their face and hands with masks and gloves. These theoretical considerations are not meant to prepare people to face another quarantine. However, let's imagine that the supernova exploded only 10 light-years away. Here the results would be catastrophic. The flash also forms radioactive iron that can cause the destruction of the ozone layer and the penetration of dangerous ultraviolet rays into the planet, which will cause the extinction of all life on the planet. Bunker will be given some time, but this too will pass. And yet we can be sure that supernova diseases do not pose a threat to humanity. The risk of giant meteorite impacts, global pandemics, climate collapse, and nuclear war is greater. Yes, there is a lot of fear in our society, sometimes unfounded and unfounded. Fear is the strongest ray that destroys us more than the strongest radiation. So we would like to have less fear in our lives, at least not fearing one beautiful universal spectacle, the supernova star. Consider our favorite gold. Its nucleus consists of 79 positive protons, so gold must spin at more than half the speed of light to keep electrons from falling inside. This makes them more massive and pulls them into narrower orbits with lower energy. In this configuration, the electrons do not reflect blue light, thus giving gold jewelry its characteristic glow. Physicist Richard Feynman is said to have invoked the theory of relativity to predict the end of the periodic table at element 137. His calculations showed that electrons in elements above 137 must travel faster than the speed of light to avoid collisions with the nucleus and violate the laws of relativity. True, recent calculations have eliminated this limit. Feynman viewed the nucleus as a single point. Let this be a ball of particles, and the elements can live up to about 173. These outliers may be atoms, but like strange creatures that can summon electrons from space. Relativity is not the only problem. Positively charged protons repel each other, so the more of them in the nucleus, the more stable it is. Uranium, with atomic number 92, is the last naturally occurring stable element on Earth. Each element then has a rapidly decaying nucleus, and their half-life is time. The time required for half of a material to decay can be minutes, seconds, or even fractions of a second. Atomic physics in the early 1930s seems to be a strange pattern. Nuclei in which the number of protons and neutrons is 2, 8, 20, 28, 50, 82, or 126 and were characterized by high stability or stability. This regularity was confirmed not only by physical experiments but also by analyzing the distribution of various elements in nature. By distribution you can judge how stable an element is. Natural reserves of elements such as tin, which has 50 protons in the nucleus, barium with 82 neutrons, and steel, which has 82 protons in its nucleus, are much larger than those of their neighbors in the periodic table. At that time, these facts did not find any explanation, and physicists began to jokingly call such a number of protons and neutrons magic. It is fortunate that this discovery was not made during the Inquisition. Then it was also noted that if both the number of protons and the number of neutrons are equal to the magic numbers, the nucleus is characterized by a particularly high stability. An example of such a binary nucleus is the isotope iron, 208, which has 126 neutrons and 82 protons. Current theory has succeeded in explaining the pattern of formation of magic numbers. Like the electrons of an atom, neutron and proton shells are formed in the nucleus of an atom. The structure of atomic shells is quite different from that of electron shells, but the most stable nuclei are isotopes with neutron and proton shells filled. Thus, a super-element with a twice-magic nucleus is predicted to be element 126. A doubly magical isotope of this element must have 184 neutrons in its nucleus. This magic number is theoretically calculated to be in the region of atomic number 126, so we will be seeing isotopes for a lifetime to study their properties. But how long such isotopes will live, days, months, years, cannot be predicted. Another area of stable isotopes is expected to be atomic number 114. Researchers face great difficulty in determining the properties of distant elements such as 114 or 126. Furthermore, there is no absolute certainty that there should be areas of stability. The most interesting search. If regions of stability are not found, current ideas about nuclear structure will have to be revised. If the prediction of the existence of new regions of stability of the elements is justified, it will open new perspectives for investigating the properties of transuranic elements as well as confirm the existence of the idea and make a great contribution to nuclear physics. Structure OF is the nucleus. Of course, heavier and more unstable elements may exist elsewhere in the universe, such as dense neutron stars. But for obvious reasons it will be difficult to study them directly, because you can quickly break down, adding to the table. But the good thing about modern laboratories is that they can achieve amazing results that unlock these chemical mysteries. Typically, new elements are created as follows. For example, we have a lighter atom called calcium. It accelerates and collides with a foil of heavier atoms. If an accelerated atom moves fast enough, its nucleus, the compact nucleus of a proton and neutrons in its center, can come into contact with the nucleus of one of the heavier atoms. If this is the case, they will combine to form a heavier element. Although a sheet of foil appears solid to the human eye, it is very different at the atomic scale. The nucleus occupies only a small fraction of the space occupied by the atom as a whole. And to create a new element, the nuclei of each atom must collide and combine. It's incredibly difficult. Here's why. If you imagine an atom about 170 meters in size, the center is a tiny grape. But there is another complication. If two nuclei are headed for a collision, they must overcome a strong repulsive force that prevents them from fusing into a new element. It is called electrostatic or Coulomb force. Only if the nuclei collide with enough energy will they overcome this force and eventually fuse together to form a new element. Let's call him Rudius. The theory so far predicts that new nuclei created in the lab will not survive long enough to form a real atom, because less than 10 trillionth of a second, a radioactive nucleus would not have time to collect electrons around it and create a new element. But things may work differently in space. The fact is that with high gravity, constant or changing temperature, new elements of matter can not only fill the table abundantly, but also reach a new level unknown to us. Yes, it is possible that black holes are composed of a complete set or nearly complete set of primordial particles that decay into energy, perhaps an indescribably fantastic conglomerate. For example, neutron stars, the precursors to black holes, are thought to have an upper mass limit of 3 solar masses. It is the maximum density of matter that is equal to the nucleus when all neutrons have all their quantum states, and these energies and forces of modern physics are known. But the combination of these energies could create something that is currently unknown to science.
Stars, the sight of the starry sky is mesmerizing. It seems that one can admire it endlessly. There are so many mysteries and riddles. But what are stars? What are space objects called? What are stars? Stars are large celestial bodies scattered in space. Some substances remain in them due to mutual attraction. Stars have high temperatures, so they emit light that can be seen by observers on Earth. Objects are heated so strongly that any substance, even metal, is in a gaseous state, and their combination is called plasma. Why stars glow? Everything depends on the temperature difference between the core and the surface. Inside a star, it can reach 10 million degrees or more. Because of this, thermonuclear reactions are constantly occurring in the cosmic object, turning some chemical elements into others. For example, hydrogen, which makes up most stars, turns into helium in their cores. Due to this, there is a brightness that can be seen by the inhabitants of the Earth. Interesting fact, a person can see the stars of 3 nearby galaxies in the sky: Andromeda, Triangle, and the Milky Way. Powerful telescopes are needed to observe distant space objects. Naming stars, people began to give names to individual cosmic bodies and constellations in ancient times. At that time, people imagined the sky as the abode of various mythical creatures, after which they were named. Most of them are still in use today. The names of the constellations of the northern and southern hemisphere are surprisingly different. Here rule not mythical creatures, but different parts of ships and sea creatures. The fact is that the scientists of the southern hemisphere were poorly known in the ancient world. Its active development began in the era of great geographical discoveries. It makes sense that many constellations of the southern hemisphere were first discovered by sailors, who named them according to their preferences. So appeared in the sky keel, stern, etc. Now scientists recognize 88 constellations. 12 of them belong to the zodiac. The brightest celestial body they have is designated by the Greek letter alpha, the next, beta, etc. Individual letters are designated by an alphanumeric abbreviation. In addition, celestial bodies are classified by color and size. For example, blue giants or brown dwarfs. Star formation: the birth of a star is the fusion of hydrogen and helium molecules into one cloud. It begins to rotate. Internal gravity appears. This fact accelerates the rotation. The outer space of the cloud gradually begins to resemble a disk and the inner space begins to resemble a spherical cluster. The temperature of the material increases, as does its density. This leads to the formation of a globular protostar. Over time, the pressure and heat increase to 1 million Oc. This leads to the fusion of atomic nuclei. At this point, a new star begins to shine. The celestial body is almost invisible to the observer's eye because it is surrounded by a powerful cloud of gas and dust. As a result of nuclear fusion, a certain amount of atomic mass is gradually converted into energy. All this time, the star is moving under the influence of various forces. They mostly revolve around galaxies or space objects with a strong gravitational field. Interesting fact, stars can be seen in space at any time of day because time there is not divided into day and night. Stellar evolution: all cosmic bodies have a certain cycle of development called evolution. The mass of stars has a great influence on this process. The heavier the object, the shorter its life cycle. Cosmic bodies with an intermediate mass, i.e., 5 to 8 times heavier than the Sun, emerge from a cloud that can be up to 100,000 light-years in size. When the temperature inside reaches 3725 C, the nebula forms a protostar. When hydrogen fusion begins, it becomes an object of varying brightness. Due to compression under the influence of gravity, the expansion process is balanced. The star begins to gain energy from the synthesis of hydrogen in its core. The formation of the object takes about 10 million years. When all the hydrogen is converted into helium, the matter under gravity becomes the core, which heats up rapidly. The outer layers expand, which quickly cool down under the influence of the external environment. This is how the red giant is formed. Next, chemical processes with helium begin. When it is completely transformed into other matter, the nucleus expands its shell as the temperature rises. This leads to the formation of a white dwarf, which can reach temperatures of 100,000 C. The products needed for heating will eventually run out, so the object will gradually cool down. After a few billion years, it will become a black dwarf and cease to exist. Evolution happens fastest in high-mass stars. It takes between 10,000 and 100,000 years from the creation of an object to the end of its life cycle. At the beginning of life, they are characterized by high temperature, bright and large. The star has a deep blue color. Gradually, it becomes a red supergiant, in which carbon is actively transformed into heavy elements. An iron core is formed. It can be up to 6,000 kilometers wide. Its nuclear radiation cannot resist gravity. When the mass of the cosmic object is about 1.5 times the mass of the Sun, the core collapses. This leads to the formation of a supernova. As it collapses, its temperature rises to 10 billion Oc, causing iron to decay in nerve cells. In a second, the core shrinks to 10 kilometers in size. Then the explosion occurs. Then there are two ways things could happen. If the remaining core weighed less than 3 suns, it would become a neutron star. The object spins and emits radio pulses. If the nucleus were heavier than 3 solar masses, it would collapse completely and a black hole would form in its place. Low-mass stars are the slowest to form. The reality is that they will slowly use up their fuel reserves. Their lifespans range from 100 billion to trillion years, so such objects are not dead yet. After all, the age of the universe has been determined to be 13.7 billion years. Red dwarfs cannot fuse with anything but hydrogen. As a result, they can't grow. Such luminaries slowly cool down and eventually become black dwarfs, after which they end their lives. Interesting fact, the first map of the starry sky was made about 3,000 years ago. Characteristics of stars. People use certain characteristics to describe stars perfectly. Brilliance. This concept was introduced by Hipparchus in 125 BC. He counted groups of stars according to their apparent brightness. The first ones are the most visible, the sixth ones are the faintest. At that time, however, it was not yet known that the distances between the Earth and other cosmic objects distort the light coming from them. Therefore, they now include a term such as true brightness when describing stars. Color depends on the temperature of the object. There are stars of blue, red, yellow, and white colors. Each spatial object has only one color. However, due to the chemical processes occurring inside, flashes of different light spectrum appear on the surface. By studying these phenomena, scientists find out what elements a star contains. Surface temperature. This is measured in Kelvin, where 0 equals minus 273.15 C. Temperature is affected by brightness, color, and mass. Magnitude. The diameter of the Sun is usually assumed to be constant. Alpha Centauri has a stellar magnitude of 1.5. Larger objects are also included. Red supergiants are 1,000 times larger than the Sun. Magnitude affects the brightness of the star. Mass. The Sun is also standard here. Alpha Centauri is 1.8 versus. Weight affects the temperature. Magnetic field. Each star is surrounded by a strong magnetic field. It is able to focus on certain areas of the target, causing flares and explosions. The faster a star rotates, the stronger the magnetic field around it. Metallicity. This indicator shows how many elements with a mass greater than helium the star contains. There are 3 generations of the metal. Scientists are still looking for the oldest 3, which has no heavy elements. Types. In addition to mass, size, etc., stars are divided into different types with unique properties. Main sequence stars. This indicator is based on the Hertzsprung-Russell diagram. In it, the stars are arranged diagonally. The brightest blue are in the upper left corner. The dim red one is in the lower right corner. Main sequence stars have the same nuclear reactions as their nuclei, namely the conversion of hydrogen to helium. The spectral class and temperature of a star depends on its mass measured relative to the Sun. Red giants and supergiants. The surface temperatures of these stars range from 3,000 to 500 K. However, they have a brighter glow. Helium is burned inside the object, which is then converted to carbon. Red and orange-colored giants are located above the main stars in the Hertzsprung-Russell diagram. They are 100 to 800 times the diameter of the Sun, and in some cases YV Canis Majoris 1024 times the diameter of the Sun. White dwarfs. They represent the final stage of stellar evolution. These are essentially the nuclei of objects that have lost their outer shells due to expansion processes. They are small in size, 100 times smaller than the Sun, and low in luminosity, 10,000 times smaller, although they have almost the same mass as the Sun. The latter is due to the high density of the matter they contain. White dwarfs are clots of plasma with an electron core without energy sources. Their luminescence is due to the wear and tear of thermal reserves. Protostar. It is a cluster of gas formed after the collapse of a molecular cloud. It still cannot be called a full-fledged star. The development phase lasts about 100,000 years. Then gravity increases and the reservoir begins to collapse. The gas gradually builds up, releasing energy. This is where the rest of the star formation process begins. Brown dwarfs. Brown dwarfs are cosmic objects that are too big for planets but too small for stars. Their mass reaches 0.8 solar energy. Their formation process is similar to that of ordinary stars, but they lack the pressure and temperature to begin nuclear fusion. They contain light elements, boron, beryllium, and lithium, deep within them. When the reactions between them stop, the object closes up and becomes a cosmic body like a planet. The possibility of the existence of brown dwarfs was proven long ago, but for a long time scientists could not observe them directly from space. The first such object was discovered in 2004 in the constellation Hydra. This is 2 meters 1207. Variable stars. Variable stars are objects whose luminosity index has changed one or more times. This may be due to internal processes and various other reasons. In the past, people considered changes in the light of space objects as supernatural. From a scientific point of view, attention was paid to this issue back in the 17th century. Since the 19th century, they have been categorized by their mechanisms of brightness change. Excitable variable stars are 2 nearby objects that sometimes cover each other from the Earth's point of view. Therefore, their brightness varies. Pulsating variable stars change their brightness due to the regular contraction and expansion of the cosmic object. This is because their gravity and internal pressure are unstable. During pulsation, the size of the emitting region changes, resulting in a change in brightness. Irregular variable stars have more complex causes of light pulsation. Science still doesn't know much about them. T-Taurus stars. This is the name given to objects that are an intermediate stage in the development of a protostar, when all of its energy is generated by the effects of gravity. They are not yet hot enough to start nuclear fusion. T-on-Taurus stars. Observers have observed gusts of wind, large spots, and bursts of X-rays. The duration of the processes is 100,000 years. Wolf-Rayet-type stars. Such stars are about 10 times larger than the Sun. They are characterized by high temperatures up to 50 K and brightness. Among other stars with similar characteristics, this type of luminosity is characterized by a special unique spectrum. The formation of Wolf-Rayet stars is still a matter of controversy. The most popular version is that they come from the helium remnants of large stars. At the moment, scientists have found 230 stars of this type. Interesting fact, on a clear night, a person can see up to 3,000 stars with the naked eye. Supernovae. Supernovae are objects in which an explosion has occurred as a result of evolutionary processes. This kind of phenomenon can be seen from a distance. For an observer on Earth, it looks like a strong and spontaneous amplification of starlight, which can last up to 10 days. Similar phenomena can be seen even during the day with the naked eye. Supernovae are distinguished from new stars by their explosive power. Neutron. If the mass of the star was less than 1/35 of the Sun, it will not become a white dwarf after the explosion, but will become a supernova. The result of this process is a nucleus. It is called a neutron star. This is due to the compression of protons and electrons under the influence of gravity. If the mass of the object was more than 3 times the mass of the Sun, a black hole will form at the site of the explosion. The radius of a neutron star rarely exceeds 20 kilometers. The object has a strong magnetic field, which is created due to its rapid rotation, 1,000 revolutions per minute. Double stars. It is a system of 2 stars that are gravitationally attracted to each other. Some objects not only revolve around each other, but also exchange the masses of their matter. About 50% of all stars in our galaxy belong to this type. Binary symbols are denoted by Latin letters. A is brighter and more massive. B is dim and bright. The structure of stars. In the universe, the stars are mostly in the main sequence stage and consist of a nucleus, corona, photosphere, and chromosphere. Thermonuclear reactions are constantly taking place in the subject's intestines. The resulting energy travels through the radiation zone. The force moves through convective regions due to burning gases. The photosphere of a star refers to its surface. This is the opaque part. Then comes the chromosphere, which has a reddish hue due to the presence of hydrogen. The corona is the outer sphere of the star. This part of the object has a high temperature and can be attached to the outer layers due to convection. Atmosphere radiation is produced in the star's atmosphere, which is visible to observers from Earth. It consists of 4 zones: the luminous and chromospheric zones, the rotating layer, and the corona. Many objects have a variable stellar wind. This is the name given to the process of the expulsion of substances contained in the atmosphere into space. The appearance of stellar wind indicates instability in the atmosphere. This phenomenon is strongest for high-mass objects. Classification. The first classification of stars was made by the Italian astronomer Angelo Secchi in 1863. He divided the luminaries into 4 spectral classes, to which, after further research, another one was added. There are now 8 of them. In addition, each category is divided into 10 types. It all depends on the surface temperature of the objects. According to the Morgan-Keenan system, mass and luminosity values are added to the above indicators. The largest star in the universe. Researchers at the Bonn Observatory discovered the largest star in the universe in 1860. However, it has only recently been fully studied. This is the star in the constellation Shields. Its radius is 1,700 times larger than the Sun. It is located at a distance of 9,500 light-years from Earth. If Scuddy was in the position of the Sun, it would have captured the first 5 planets and entered the orbit of Jupiter. Technological capabilities are improving every year. Perhaps in a few years people will find a new, larger star. The smallest star in the universe, the nearest star, is the red dwarf Proxima Centauri. Its size is modest to 3 times the mass of the Sun and 200 kilometers across. It is about half the size of Jupiter, but the structure of these objects is different. A star heavier than a planet. Proxima Centauri is very faint. You can see it in the sky only with the help of special equipment. Interesting fact. The smallest star visible to the naked eye is 61 Swan. Its mass is 66% of the mass of the Sun. Which star was the first? Scientists believe that the universe originated from the Big Bang 13.7 billion years ago. At first, the temperature in space was very high, which did not allow the formation of stars and other objects. After a few million years, it shrank. Gravitational forces began to pull hydrogen and helium together. Then it was time to achieve the perfect temperature and pressure ratio. Hydrogen began to synthesize into helium. Because of this, stars accumulated to a large mass up to 150 solar masses. That's how the first generation was born. After a few million years, most of them exploded. But during their existence, they managed to form heavy elements, which flew into outer space after their death. This, in turn, led to the formation of stars as people observe them today. Observational history. The starry sky has fascinated people since ancient times. At first it was given mythical properties, then mankind learned to use it for practical purposes. For many centuries, sailors from different countries steered their ships by the stars. People have always been curious. They wanted to study the starry sky, to understand the laws by which the stars move. Therefore, astronomy is considered one of the oldest sciences. Technological progress has not stopped. Telescopes and other necessary instruments appeared. In the 17th century, the law of gravitation and motion was discovered. Over time, people realized that many stars are similar to the Sun and, therefore, obey the same laws of physics. Photography and spectroscopy analysis of light waves coming from an object appeared in the 19th century. It allowed people to penetrate into the composition of the stars and understand the basic principles of the movement of the luminaries. In 1937, the first radio telescope was created, which allowed the study of radiation from stars. This allowed astronomers to better study the internal structure of space objects. 1990, the first Hubble Space Telescope was launched. This allowed scientists to study areas inaccessible to observers from Earth. Solar system. The Sun has a tremendous gravitational force that allows it to hold the planets close to it, forming the entire system. They orbit each other and have certain characteristics depending on their location. Scientists are constantly exploring the solar system and are constantly making incredible discoveries that help us better understand the structure of the cosmos. What is a solar system? The solar system is a collection of planets orbiting around a central star. Scientists have been able to determine that it is approximately 4.57 billion years old and was formed by the gravitational compression of a cloud of gas and dust. At the heart of the system is a bright star, the Sun, which contains planets and other objects. Make them rotate a certain distance. Its diameter is several times larger than other gravitational field objects. Interesting fact, the mass of the Sun is so great that all the other planets in the system are only 0.14% of its mass. In addition to the star, the solar system has 8 large planets and 5 dwarf planets. It is located in the Milky Way galaxy below Orion. Formation. Since the solar system is billions of years old, people can only speculate how it formed. The most popular is the fog theory, which was introduced by scientists Laplace, Kant and Swedenborg in the 18th century. It is based on the fact that the system was formed by the gravitational collapse of one part of a huge cloud of gas and dust. The hypothesis has since been supplemented by space exploration data. The process of formation of the solar system is now described by the following steps. 1. In the beginning, in this region of the universe was a cloud of helium, hydrogen, and other substances formed by explosions. Old stars in a small part of it began to compact, which became the center of gravitational collapse. Gradually, it began to attract the surrounding subjects. 2. Because of the attraction of matter, the size of the cloud began to decrease and the speed of rotation increased. Its shape gradually changed to a lamellar shape. 3. As compression increased, the density of particles per unit volume increased, causing the matter to gradually heat up due to repeated collisions between molecules. 4. When the collapsing center of gravity heated up to several thousand Kelvin, it began to glow, indicating the formation of a protostar. At the same time, other condensates began to form in different regions of the disk, which in the future would serve as centers of gravity for the formation of planets. 5. The final stage of solar system formation began when the temperature of the center of the protostar exceeded a few million kelvins. Helium and hydrogen then underwent a fusion reaction that led to the birth of the perfect star. The remaining compacts of the disk little by little formed planets that began orbiting the Sun in the same direction, being in the same plane. This process took a very long time, and scientists can only guess how many years it took for the solar system to form. Structure of the solar system. At the center of the solar system is the Sun, which is composed of helium and hydrogen. Its surface temperature is about 6,000 degrees Celsius, and the sphere is many times the size of other objects in its gravitational field. The star is a yellow dwarf. Interesting fact, the Sun attracts objects to light years away. It is about 18.9 trillion kilometers across. At different distances around the star are the planets, which scientists divide into two groups: terrestrial planets and gas planets. Earth group planets. The Earth group is closer to the Sun. Its planets have a rocky texture and high density, making them smaller than the gas giants. Mercury, the closest planet to the Sun, is also the smallest planet in the system. It has a radius of only 440 kilometers. It gets its name in honor of Mercury, the god of commerce. Its surface is gray, which is why many people compare it to the Moon. The planet has no satellites and is almost completely devoid of atmosphere by strong solar winds. Venus, the second planet from the Sun, is named after the ancient Roman goddess of love. The peculiarity is the absence of natural satellites and a high concentration of carbon dioxide in the atmosphere. The radius of Venus is almost identical to that of Earth, 6,051 kilometers, which is only 5% less. This is why the planets are called brothers and sisters. However, Venus is very different in appearance, as it resembles a milk bowl. The surface consists almost entirely of petrified lava with rare meteorite craters. Earth, the third planet from the Sun, the only one whose territorial areas are filled with water. Due to favorable climatic conditions and sufficient resources, it is the only source of life in the solar system. The planet has a radius of 6,378 kilometers. Mars, red planet, is the farthest from the Sun and belongs to the Earth group. It is also considered the smallest after Mercury. Its radius is 3,396 kilometers. Earth consists mainly of sandy and clay landforms that are divided into light and dark areas called continents and seas. Mars is of great interest to scientists in the 21st century. Since the planet is relatively accessible, Mars rovers are regularly sent out to collect data. Gas group planets. This group consists of 4 gas giants that are farther from the Sun than the other planets. Its huge size is due to its low density composition and large amount of gaseous matter. Jupiter, the largest planet in the solar system. It has a radius of 69,912 kilometers, which is almost 20 times the radius of Earth. Scientists still cannot determine the exact composition of the planet. They only know that it contains more xenon, argon and krypton than the Sun. Jupiter also has 67 satellites, some of which look like planets. For example, Ganymede is 8% larger than Mercury, and Io has its own atmosphere. There is also a theory that Jupiter was meant to become a full-fledged star, but remained a planet during its developmental stage. Saturn, the 6th planet known for its icy rings and rock meteoroids. Saturn has a radius of 57,360 kilometers. Scientists have not yet studied in detail the composition of the surface, but were able to show that it contains almost the same chemical elements as the Sun. There are 62 satellites around Saturn. Interesting fact, rings have recently been discovered in other gas giants besides Saturn, but they are not so remarkable. The reasons for their appearance can only be speculated at this point. Uranus, the third largest planet in the solar system. It has a radius of 25,267 kilometers. Uranus has a temperature of minus 230 degrees Celsius, making it the coldest planet. It also has a unique feature. The axis of rotation is located at an angle, because of which the planet gives the impression of a rotating sphere when moving. The surface consists mostly of ice with small amounts of helium and hydrogen. Neptune, the eighth planet from the Sun, was discovered not by observation, but by mathematical calculations. Observing the anomalies in the motion of Uranus, scientists have suggested that they are caused by the presence of another large celestial body. Neptune has a radius of 24,547 kilometers. The surface is similar to uranium, but is driven by the system's strongest winds, accelerating up to 260 meters per second. Order of orbits: each planet has its own particular orbit in which it revolves around the Sun. The time it takes for it to return to the same point after coming full circle is called a year, most often measured in Earth days. Mercury is closest to the Sun, which makes it orbit the Sun in the smallest orbit, and it has a year of 88 days. Venus makes a complete revolution around its star in 224 days. For Earth, a year lasts 365 days. Mars takes almost twice as long to complete a full revolution as the third planet, 687 days. Jupiter, which is the nearest gaseous giant to the Sun, has a year's duration of 4,332 days. Saturn makes a complete revolution in 10,759 days. That's nearly 30 Earth years, being practically the farthest planet from the Sun. Uranus completes a circle in 30,685 days. Neptune has the largest orbit and has to travel the greatest distance during its year, which lasts 60,190 days, almost 165 years. Also, each planet rotates around its axis at a certain speed, which makes the length of the day on them different. Is Pluto part of the solar system or not? Since the 19th century, scientists have hypothesized that there is a ninth planet in the solar system that is farthest from the Sun. In 1930, 23-year-old Clyde Tombaugh, an employee of the Mount Wilson Observatory, succeeded in finding Pluto. He did this by regularly photographing the starry sky and looking for moving elements. The object was found in the Kuiper Belt region. In the same year, Pluto was officially declared the ninth planet. Due to a lack of data, it was compared in size to Earth, but further research revealed that it had a radius of only 376 kilometers and a mass 6 times smaller than that of the Moon. The planet's surface consists mostly of rocks and ice. Like most Kuiper Belt objects, Pluto has 5 satellites. The orbit around the Sun has an oval shape, and at maximum approach the planet is closer to the light than Neptune, and at its greatest distance the distance is 7.4 billion kilometers. During further studies of the Kuiper Belt, scientists found several other small planets, the size of which is not much different from Pluto. In 2006, it was decided to dwarf them. Pluto has since officially ceased to be the ninth planet in the solar system. However, some scientists still insist that it should be moved back from dwarf to major. Other objects: in addition to the Sun and planets, there are other objects in the system. These include dwarf planets that are inferior in size to the major planets. Kuiper Belt, a disc-shaped region containing many icy bodies. Located beyond the orbit of Neptune. Oort cloud, a cluster of icy conglomerates. Comets, formations of gas, dust, and ice moving through space. Asteroids, rock formations traveling between Mars and Jupiter. Meteorites, small solid objects that fall to the Earth, turn into meteors when they hit the atmosphere, and burn up before reaching the planet's surface. Sometimes asteroids and comets from neighboring galaxies can fly into the solar system, but this phenomenon is quite rare. The Oort cloud is outside the solar system. The Oort cloud is located around the solar system and the Kuiper Belt. Its inner limits begin at 200 to 500 U. Its distance from the Sun and outward is 100 to 200 U. To facilitate study, researchers divide the region into outer and inner parts. The cloud is made up of trillions of particles consisting of ethane, water, methane, ammonia, hydrogen, and other substances. Among them there are rocky asteroids, which make up 2% of the total number of objects. Almost all bodies are less than a kilometer in diameter, with dwarf planets being a rare exception. Interplanetary space: many people think that there is nothing between the planets. However, this assumption is incorrect. The Sun constantly emits charged particles that travel through space at 1.5 million kilometers per hour and form the heliosphere. This current is called the solar wind. If an object doesn't have its own magnetic field holding back the atmosphere, the charged particles will literally tear it apart. A similar fate befell Mars and Venus. Colonization in the 20th century, space was actively explored not only by observing it in a telescope, but also with the help of various satellites, shuttles, rockets, etc. For life, unfortunately, a cataclysm may occur on Earth at any moment, so mankind needs to find a new home. Therefore, the possible colonization of space is not an empty sound for modern observatories. In the last century, probes have been sent to various planets and have continued to relay information about their journey. This helps to better understand the structure and properties of objects of the solar system. As for direct colonization, sending Mars rovers to circle the surface of the Earth's satellite and the fourth planet in search of life and other unusual discoveries is already the order of the 21st century. However, now humanity is only on the threshold of space travel, so it is not necessary to talk about a possible flight to another planet. Moreover, most of the large bodies of the solar system are unsuitable for life. Why the solar system is stable, all the planets revolve around the sun in their orbits, without touching each other in any way. They are also constantly affected by the attraction of the stars, which is based on the law of universal gravitation. And since there is no friction in space, the planets move at a constant speed, and for billions of years the solar system has enjoyed enviable stability. Earth's place in the solar system can be called the most favorable, since life originated on this planet. The third planet revolves around the star on ellipsoids. The maximum distance between the Earth and the Sun is 152 million kilometers and is called aphelion, and the minimum distance is 147 million kilometers and is called perigee. An interesting fact is that while traveling, the Earth reaches aphelion in June and perigee in January. At the intersection of these points, the planet begins to experience a steady cooling or warming. Due to its favorable location, the Earth is constantly warmed by the sun's rays. Depending on the season and location, the surface temperature varies from -89 to 57 degrees Celsius. This is sufficient for the origin and development of life. The solar system's place in the galaxy. In the Middle Ages, it was believed that the Earth was the center of the universe. Since it was impossible to estimate the size of the room at the time, this assumption seemed the most logical. It was later discovered that the planet is just a part of the solar system centered in a giant star. And even later, it became known that this is only a part of a large galaxy, the Milky Way, which, in turn, is one of many in the universe. Scientists have created a global map of the Milky Way. It encompasses all known boundaries and has a total width of about 100 light-years. For convenience, the galaxy is represented as a flat disk. The solar system is located almost sideways, 28,000 light-years away from the center. Exploration of the solar system. Since the middle of the 20th century, people have been actively trying to explore the planets of the solar system. In 1957, the Soviet Union launched Sputnik 1 into Earth orbit. He spent several months in space gathering information about the planet. Over the next 2 decades, up until the 1980s, people sent travelers to most of the planets in the system, taking many close-up photographs. This helped to create detailed descriptions of objects and study composition. Now everyday scientists receive a lot of information about the planets of the solar system, which is transmitted by dozens of satellites. Why do the orbits of the planets lie in the same plane? In the solar system, the star and planets are on the same level. Only a few orbits are slightly tilted. Scientists believe this is because the objects formed at the same time and from the same material. During the collapse of the galaxy when the solar system was born, the gas cloud gradually narrowed and turned into a rotating disk. Therefore, when the planets of the future began to turn into condensation, they were already at the same level. The motion of the planets around the sun. The ancient Greek astronomer Ptolemy was the first to suggest that the planets and the sun do not remain stationary, but rotate in their orbits. However, due to lack of technology and knowledge, scientists believed that all objects revolved around the Earth. Nicolaus Copernicus hypothesized that the planets revolved around the sun. He built his own model of the solar system and, on its basis, wrote the rotation of the celestial balls. The work was published in 1543 in Nuremberg. Sometime later, Kepler showed that the orbits of the planets are not circular but ellipsoidal. In 1687, Newton discovered the universal law of gravitation, which explained the interaction between the planets and the sun. Interesting fact, Newton's law helped to prove that the tides on Earth are caused by the activity of the moon. Now people have enough knowledge and technology to predict the exact trajectory of any planet. Based on this information, rockets and satellites are launched to meet the target at a certain point in space and after a certain time.